Okay, so in this video, I'm going to just have a quick talk to you about some of the features of graphs that are involved with gravitational potential and electric potential, and this idea of equipotentials. So what is an equipotential? Well, let's just take Earth, for example. Here we go, we've got the field lines coming in here. Remember, because if we stuck a mass in this field, it would travel in that direction. So, what is a equipotential? Well, an equipotential is a region that indicates the potential at a point where all the potentials are the same. And they're based on the radius, because remember, equipotential, or a potential in a gravitational field, is equal to gm over r. So it's based on a distance r. So based on that distance r, we can create potentials. Now, apologies for my poor drawing. Or that green line I've drawn there should all be at the same distance r. And the point saying that is the fact that we're saying that the potential at any point on this circle is exactly the same. That means something very profound. It means it takes no work done to move the object to any other point on that line. So if I move an object from here to here, it takes no work done. There's no work done required. The only time work done is required is when you move from one equipotential line to another. So say I have another line of potentials at a different distance r. Well, it's going to take work in order to move it from one potential line, equipotential, to another. And that's all there is to know about equipotentials. They work exactly the same for gravitational as they do for electric. So here's the electric one, kq over r. And so it takes work to be done to move them from potentials. And one thing you'll notice about potentials, the same as you'll notice about field lines, is that field lines, when field lines are close together, that indicates, close together field lines indicates a strong field. The same thing means for equipotentials. Close together equipotential lines equals a strong field. So in terms of that field, it's useful to look at how we can relate field strength to potential, not just in kind of calculations, but sometimes graphically as well. So graphically, we can say that if we look at each situation in turn, so we're going to look at gravitational first, just to really hammer that home. So gravitational potential. So if we were to look at a graph of gravitational potential against radius, notice it's a negative value because gravitational potentials are negative. The graph looks something like this. Okay? Because it's inversely related, so because Vg is equal to Gm over R. So we would expect to see this nice inverse curve, inverse relationship curve. It would be a straight line if I did 1 over R or something like that. But the interesting thing with this is that we can actually use this graph to determine a number of different things. Well, not a number, one very important thing. Sorry. The gradient at any point on this line is equal to something really important. Well, let's look at what the calculation is we're doing here. We're doing Vg over R. let's look at what that means. So VG is GM over R divided by R. Well, that's just equal to GM over R squared. Whoa, look at that. What's that? Well, that is the field strength, G, at that point. So the gradient of a VG against R graph is the field strength. You can actually tell the field strength by taking a tangent to the curve at any point along this graph. So if you've got one of these graphs, you can actually determine the field strength at a very specific point, which is really, really cool. So what can we do with the electrical ones then? Well, we can do pretty much exactly the same thing. So electrical potential, very similar equation. So we got VE is equal to, just remember I missed the minus sign off there, don't forget that. VE is equal to KQ over R. Well, notice that this is positive this time. So that means actually we could have two graphs. So VE, radius. Notice that this would be still a curve, and so would this. But why have I got two different graphs? Well, this is an attractive field, isn't it? Because mass acts to attract. So this is the graph that you have when you have a positive and a negative, or a negative being attracted to a positive, or a positive being attracted to a negative. This is an attractive graph. And again, gradient of that line equals the field at that point. Really fascinating. Same with this one. Instead of having, this is a repulsive, remember? So this is a repulsive field. So instead of having two opposite charges, you might have two like charges which are repelling each other. The gradient of this graph is also the field. Let's just prove that to you. So I'm doing VE over R. Well, VE is KQ over R divided by R. Well, if I rewrite that, that's just KQ over R squared. Voila, that's the field strength. That's the electric field strength at any point in that field. So again, a really, really useful observation to make from these graphs here. There's just one more observation I'd like to make, which actually is in reverse to these right here. Since it's my last sheet of paper on this pile, it's probably a good job. So there's one other graph you need to be aware of. Now, depending on what graph you've got and what you're dealing with, you can also have a graph of force against distance. Now, it's worth noting that force against distance, in this case, it shares a very similar graph with field. So you could have the field strength or G. So this would be electric field strength, this would be gravitational field strength, or we can just deal with force. We're going to focus on force for the moment, and we're going to use the force idea to talk about that. So again, the graph is something like that, a nice curve, but it's actually a inverse square, because remember, force is equal to GM over R squared, so that's why I've drawn this a bit steeper. But what's really, really telling about this is that what we can do here is we can actually say that the area under this graph is the work done. Well, that is the work done in bringing it from infinity to that point. Well, look at that. That's the same definition that we had for both electric fields and for gravitational fields. So a nice observation here is that the force, the area under this graph, force times R, is equal to the work done by that. And actually, that makes a lot of sense, because remember, work done, from our most simple equation of work done, is force times distance. Well, force and distance. So that's really nice. So the idea with that one is that you could I'm just making a point of showing you that you can get the work done, that same work done that you work out from or you can get from a force against R graph in this case. So really useful to draw, really useful things to see, lots to take notes on, lots to practice there, and we'll have a go at that in class.